Hey, welcome back, Ace Trig students. Mr. Meunier here. Thank you for submitting your Section 9.1 Intro to Polar homework in Schoology. If you have not done that, that needs to be done by 11 a.m. Wednesday, 11 a.m. That is the completion grade. Today, we're going to continue in Section 9.1, working with our new polar coordinate system, but discuss how can we turn a polar coordinate problem into our more traditional rectangular coordinates, or vice versa? How do we turn rectangular into polar? Remember from Monday, we discussed how polar coordinates are based on a circle and an angle, and we use r for the radius of that circle and theta for the angle at which that point's at. Rectangular coordinates are traditional grid system where we use x for the horizontal distance and y for the vertical distance. The radius is the distance from the pole, and x and y is the distance from the origin on a rectangular grid. We can take a polar coordinate system and impose it onto a rectangular system, literally, like I have just circled in this picture, and we can see if the pole and the origin line up. If the 0-degree polar axis and the positive x-axis line up, we can easily change a grid problem into a polar problem. And that's what we're going to talk about today. How do we do that without having to draw pictures constantly? What formulas can we use to get there? And it's all going to come back to your right triangle work with some SOHCAHTOA. That kind of never goes away. Big thing we discussed on Monday was that polar coordinates are not unique. When I say that, I mean that there's an infinite number of ways in which you can represent a single polar point. Polar coordinates are not unique. But in our grid system, rectangular coordinates are unique. If I say x is 3 and y is 2, there is not another way to represent that. So rectangular coordinates are unique. Polar coordinates are not, rectangular coordinates are. Alrighty. So if we have a point in the polar coordinate system, point P out here, and I know what the radius is. I know how far that point is from the pole, and I know the angle at which that is moving, the angle at which you have worked through to get there. We can figure out its XY coordinate because the X is the horizontal and the Y is the vertical. And if I draw a horizontal and a vertical literally, we make a right triangle. Within that right triangle, if I want to know what the x coordinate is, I have this angle theta. X is adjacent to that angle, and r happens to make up the hypotenuse of the right triangle. And hopefully remember, adjacent and hypotenuse is the cosine function. So the cosine of our angle is the unknown x adjacent side over the known hypotenuse radius side. And if I want to deal with the vertical, the y piece, well, y is opposite of our known angle, and the radius is still the hypotenuse of this triangle. Opposite and hypotenuse with a right triangle is your sine function. So the sine of the known angle theta is the unknown opposite side of y over the known hypotenuse side of radius. If I multiply the r over, we get r cosine of theta is your x, and r sine of theta is your y. So these two formulas will help us turn radiuses and angles into an x or a y piece. So how do we do this? These can be done in radians or degrees. Read carefully. This says find the rectangular coordinates, which again means find the x and y, express as an exact value when possible. That just means if we know our trig values for that angle, use those known trig values. Otherwise, round it to the nearest hundredth. So on this one, we have a radius of 5 and an angle of pi over 3. That angle is in radian mode. Pi over 3 is an angle that we should know trig values for. That was from our unit circle quizzes. So let's do this as an exact value. Again, the x coordinate is going to be the r times the cosine of the angle, and the y coordinate is the radius r times the sine of our angle theta. So x is going to be 5 times the cosine of pi over 3, while y is 5 times the sine of pi over 3. Hopefully we remember our hand trick, or we just remember our unit circle values from January and February. And we know that cosine of pi over 3 is radical 3 over 2, while the sine of pi over 3 is 1/2. That gives us x being 5 radical 3 over 2, y is 5/2. So we can write that as an ordered pair, 5 radical 3 over 2, comma 5/2. That's our x and y. Part B here, Q, negative 13 and 70 degrees. Again, this is the radius, 70 degrees is the angle. We're going to have to round this one because 70 degrees is not a value that we know from our unit circle problems. But we can say x is negative 13 times the cosine of 70 degrees, while y is negative 13 times the sine of 70 degrees. But I need to get a calculator out for this. Make sure your calculator is in degree mode. I'm going to change that to degrees. And we're going to say negative 13 cosine of 70 gives us about negative 4.45, and negative 13, the sine of 70 is roughly negative 12.22. Negative 4.45 and negative 12.22, I believe. Yes. That might not make sense if you look at this point, negative 13, 70 degrees. A lot of people say, hey, 70 degrees, that's in the first quadrant. But remember from last class, we discussed how if 70 degrees is out here, you find the angle first when it comes to polar, and then the negative 13 radius tells you to go away from that angle. So point Q is really going to be opposite of that 70 down in this third quadrant, where, yeah, negative 4.45 and negative 12.22 do make a little bit of sense. All right. So that's converting polar points into rectangular coordinates. If we want to go the other way around, we still need to use some triangle, right triangle ideas here. So if we know what a point is in XY terms, here's a point XY, we can make a right triangle out of that. While X is the horizontal, Y is the vertical, and now the hypotenuse is the radius of that. And if I know two sides of a right triangle, that's Pythagorean theorem, where x squared plus y squared is r squared. Take the square root, and your radius is really just radical x squared plus y squared. And if we want the angle, theta, if I know the opposite side is y and the adjacent side is x, well, tangent uses opposite over adjacent. Tangent of theta is y over x. So the angle is the inverse tangent of y over x. Now, we discussed last unit with vectors, and it still holds here. Inverse tangent doesn't work in the second or third quadrants. So if you happen to have a negative x value, you need to add pi or 180. It's going to put plus 180 degrees or pi, depending on what type of unit we're measuring this in. Degrees is 180, pi in radians, and we only do that if our x is less than 0. Your x value is a negative. You need to add those onto your angle. All right. So now we want to find the polar coordinates of r, -8, -12, round to the nearest hundredth. In this one, they don't tell me the unit in which to do the angle in. I'm just going to say, let's do this in degrees. It'll be clear on quizzes, tests, homework, etc. What type of unit we want our angle to be measured in. In this, my -8 is the x, -12 is the y. I got to figure out, find the polar. What is the r and the theta going to be? R theta is the unknown here. So the radius is radical -8 squared plus -12 squared. Go to my calculator. Radical -8 squared plus -12 squared. That's going to get us, well, I wanted this in decimal form, 14.42. For radius. And then my angle is the inverse tangent of my y value of -12 over my x value of -8. Since the x is negative, since that x is a negative number, I need to add 180 to my answer, 180 degrees. If I was doing this in radians, I would add pi to my answer, because 180 and pi are equivalent. So I got to go to the calculator. We're going to go inverse tangent of, let me double check it, -12 over -8. Oops. And I'm going to add 180 to that, giving us 236.31 degrees. That gives us a point in polar form of 14.42, comma, 236.31 degrees. And that does make sense. If you think about a dot at -8, -12, R somewhere down in the third quadrant, 236 degree angle, that's in the third quadrant with a 14 degree radius, 14 unit radius going towards that. If you didn't add 180, you would have had approximately a 56 degree angle, which would not have made sense with this particular point. So moving on, find the polar coordinates of a point whose rectangular coordinates are radical 3, 1. Again, nothing says you have to use radians here. I'm just going to do that to show you that, yeah, we can use radians as well. And I want to do this as an exact value. Since the directions did not specify any of that in this problem, you would not be penalized if this was an actual problem if you didn't do radians or exact values. Test, quiz, homework will be clear on what type of unit and how we want the answer to be presented in the future here. But I do know that x is radical 3, y is +1. Find the polar coordinates of this. So the radius is radical 3 squared plus 1 squared. That's going to be 3 plus 1, which is radical 4, which equals 2. My angle is the inverse tangent of y1 over x radical 3. It's a positive radical 3 for the x, which means I do not need to add pi to this. That is okay as is. If you clean up that fraction of 1 over radical 3, rationalize it into radical 3 over 3, that's a tangent problem we should know. And tangent equals radical 3 over 3 at a pi over 6 radian angle. So we have a solution of 2, comma, pi over 6. Okay, so that was converting points back and forth, individual spots on a curve back and forth. We can also do entire equations. If we're converting equations, you want to use these formulas. I'm going to write them out here. Use the fact that we know x is r cosine theta. Use y equals r sine of theta. Use r is radical x squared plus y squared. Use r squared equals x squared plus y squared. These are kind of the formulas from the boxes, the previous problems. Do not use, oops, do not use theta equals the inverse tangent of y over x. Do not use that one. So if we're going to turn r equals 6 cosine theta, a polar equation, into rectangular form, kind of the rules I want to go by here is we want to get rid of, change all the r's and thetas into x's and y's. Change r theta into xy. We're going to use formulas to do that. That's really the main thing here. So if I look at this problem, r equals 6 cosine theta, the r piece, that is radical x squared plus y squared. That makes sense. We could do that. The issue is the theta piece. We don't have a good substitute for theta because I do not want to use this inverse tangent. The cosine of the inverse tangent of y over x is messy. But if I have theta with a cosine, we can make this work if there's an r in front of it. So a common somewhat trick on these problems is multiply everything by r, and they tend to simplify better. That doesn't happen for every single problem, but it is a fairly common trick on these. If we multiply the left side by r, that gives us r squared. If you multiply the right side by r, that's 6r cosine theta. Now we're in business because r squared is x squared plus y squared. We can make that substitution. We have a number 6, and then r cosine theta is x. And we're good. As long as r and theta is no longer part of the problem, it's just x and y, we're in good shape. Done. That's the rectangular equivalent. All righty. So, other way around. Write the rectangular equation, x minus 3 quantity squared plus y squared equal 9 in polar form. So this time, we want to turn xy into, change xy into r and theta. And again, we're going to use formulas to substitute. And then on these, I do want you to solve for r at the end. We could say x is r cosine theta and y is r sine theta right off the top. That gets a little bit tough to deal with algebraically. I recommend we kind of FOIL this out in xy form first, because we're used to simplifying in these terms. So x minus 3 times x minus 3 as a FOIL problem is x squared minus 6x plus 9 plus y squared equal to 9. The 9 and the 9 cancel out, and we kind of have an x squared plus y squared minus 6x equal to 0. Now this is nice because up above, it's not on my screen now, but x squared plus y squared as a unit always equals r squared. So that took care of those. We have a minus 6, and x as a single all by itself is r cosine theta equal to 0. So all the x's and y's are gone. We have r and theta instead. My last thing is let's get r isolated by itself. If I move the 6r cosine over, we have r squared equals 6r cosine of theta. We can divide through by r or cancel an r away from each side, and r is 6 cosine of theta. All right. So last, like above, turn the y squared equals 4x, your rectangular xy equation, into a polar r and theta equation. There's really nothing to FOIL or combine or simplify here to get started. So let's just try to substitute in the fact that we know that r, whoops, we know that r is, or excuse me, we know that y is r sine of theta. So r sine of theta, all of that is squared, and that equals 4, and x is r cosine of theta. If we square this, we get r squared sine squared theta equal to 4r cosine of theta. I want r to be isolated. We can divide through by r, cancel an r away from each side. So r sine squared theta is 4 cosine of theta. Divide the sine squared over, and we have r equal to 4 cosine of theta over sine squared of theta. And then this can simplify a little bit, because sine squared is really sine theta times sine of theta. And we did in a previous unit, chapter 7, cosine on top of sine is cotangent. 1 on top of sine is cosecant. So 4 on top of sine is 4 cosecant. So r is going to be 4 cosecant theta, cotangent theta. All right. That pretty much does it for converting rectangular points or equations back and forth. Your assignment, there is a section 9.1 polar rectangular Schoology assignment. That's a completion grade. It will self-grade it for you. You can have 2 tries if you want to do it again and get better the second try. Please have that done by Friday at 11 a.m. That assignment has some true false, some multiple choice, some fill in the blank, and some matching. These equations back and forth, the last part of the notes here is set up in a matching form, which might make it a little bit easier on us. If you got any questions, please let me know. Friday, you will have a small quiz over the 2 things we went over this week. Hope everybody's doing well. Hang in there. It's almost summertime. Later.